I will go through this as simply as I can to start with. Graphs are actually not that difficult to get into. So it's one of the reasons why it's a topic within Math 125, although I realize not everybody gets that, and it depends on the teacher. So it is one of the topics near the end in that course. It's one of my areas of specialty. I think it's really enjoyable just because I can draw them. So I mentioned a little bit at the beginning of the semester some of my background. I won't reiterate any of that. I've got the main application code, which is, of course, supposed to always look nice and clean. We've got our abstract data types, and we want to design them so that when we go to write the other code and we make use of our data structures, we don't have to struggle to really understand what's going on, and we take advantage of all the hard programming that went into making them. I'm going to draw this for you. So I'm going to run it, and we'll take a look at the output, and then I'll give you some pictures to help explain what's going on before I go diving into any of the other code for a graph data structure. There is another algorithm that I've got below we'll get into later. So breadth first search. I know the name is a mouthful, but you'll find that the way we can program this is very much like the simplification that we had for the first few questions on the midterm. We learn about the really complex data structures and try to practice programming those, but then when you're actually solving problems, you can do it pretty quick. So the code for breadth first search will look something, and will probably remind you of the kind of code that you had written and the solutions that I provided before for the midterm for those first few questions. So let me go, I think I've got a terminal open. Okay, not yet. Okay, if we've got, it should be compiled. If I just do Java app, you can see just the data corresponding to the graph, and I've created an instance of a graph on line 4, and then I connected nodes in the graph. So when I start drawing the picture, I'll explain some of the vocabulary for it. And each node has a linked list associated with it describing the connections to the other nodes in the graph. So if you're into networking, you'll probably really enjoy thinking through the theory of graphs. And we really only scratch the surface because we just want to be able to program with them here. And then I've got the output for the breadth first search algorithm that ran, and we get back a tree. So we've talked about trees of different kinds throughout the semester. And I'll draw a picture for this as well, just to explain the output of the breadth first search based off of the input graph G to get our tree back T. So I'm gonna pause, and when I come back, I'll have the pictures for both of these graphs up. Okay, so just a quick explanation with the picture. I've only got the graph G drawn here, and then we'll do the output for breadth first search after. So we've got the output on the right hand side, and I'm looking at the linked list, just one linked list at a time. If I'm considering the node 0, which I've got right over here, what other nodes is it connected with? We've got node 1 and then node 2. So you can see the two edges making the connections. So just a quick reminder of some of the basic pieces. And then of course you can go through and you can see the other linked lists for the other nodes. So node 1 is connected to its neighbor 0, as well as another neighbor 2, and then node 2, we've got 3 neighbors, so it has degree 3, and node 2 is connected to every other node in the graph. And then node 3, it's only got the one neighbor, node 2. So very, very simple graph. Only 4 nodes like this. There's only so many different kinds of unique graphs with very few vertices that you could actually draw all of them. And if you did that and tried to write down the linked list corresponding to each node, if you did that for each graph, it wouldn't take you too long. You could probably just fill one piece of paper. You'd draw it quite a bit smaller than what I've done on my screen here. And it would still be decent if you're just writing regular size on the piece of paper for the numbers like you would normally do for regular size writing. You could probably fit all of the graphs if you were thinking about all the different kinds that you can have on 4 nodes. Sometimes you'll hear me lapse into some of the other vocabulary. So a node you can also call a vertex. So you'll just have to forgive me if I tend to slip into that vocabulary, because that tends to be more common in mathematics, which I've got a much stronger background doing research in mathematics. And then I spent quite a bit of time during my PhD doing programming for graphs. So the data structures we're looking at in Java were mostly supported by the linked lists that you could program. And I'm going to be providing that for the code for this week. And then I'll just briefly go over the code, and you would write the code for graph, which is actually not that much to write. You've got most of the functionality from the linked lists. The other thing I would like to do this week would be, I'll probably have a video tomorrow and go through the visualization. So I've done it for trees. I'd like to do the same thing for graphs, and I'll provide that code. So then in your own practice, you'd be writing the code for the graph, and then double checking that you've got a nice graph code written, and you could check it with the visualization. And you could get comfortable deciding where you would want to place your nodes, your vertices. Because you can draw them on paper like this, you get a choice for the location of each node. It will be ordered pair. So you've got the x-axis, the y-axis. So you have to decide where you would like to give a location for each node as well. That would be a little bit more data that you would store in the data graph to then be able to visualize it. The visualization code is not going to be too much different from what we had for trees, because trees are also graphs as well. Okay, I'll come back with a drawing for the breadth first search tree for the graph G, and then I'll just briefly discuss what's going on with the algorithm. Okay, so I also wanted to expose a bug that I've got, just to keep reminding everybody that when you're programming, you always have to think about the results of your code. Are they actually doing what you want them to do? So just taking a look, I just want to make sure you can see we've got the output for graph T. We've got the list for neighbors for node 0. Oh, look at that. We've got the node 0 itself listed. Can you have that? Well, there's nothing stopping you in a graph from having what's called a loop. And it just means that you've got one of these edges or connections where the node is connected to itself. But in terms of what I would like for the results for depth first search, I want a tree, and I don't want any cycles. So if I could traverse nodes by in sequence using edges to start at one node and then return back to that node in a cycle, then it's not a tree. So I would also want to remove loops. when I'm considering trees like that, because it would be like a trivial cycle. So I go over in my picture and I would want to get rid of my loops. So that would mean in my code, I'd have to do a little bit of debugging, and I'd have to make sure with my graph and when I'm doing depth first search, I don't want it to build the resulting tree for the breadth first search. I should be able to get the result of a tree where I can traverse to any other node in the graph. If my original graph, the input, if it's completely connected, I could visit from one node and use edges in sequence to then travel to any other node if it's completely connected. So in my tree, I want only just edges where there's not going to be any cycles. So I'm not going to have anything that looks like this, where I've got the three edges, 0, 1, 2, and then I could traverse back to 0 in a big cycle. And I wouldn't want that for my tree, because we don't have that as definition for trees. It can't have cycles. But it also needs to be connected. So breadth first search, you're going through in your algorithm, you start at some particular node that you're interested in. For my input, I gave it the node 0. So we started here, and then in the breadth first search, you're using a queue, and we can just have an array to do that. And to have a queue, all you need are 2 index. And you point one at the front of the queue, and you point the other index at the end of the queue, so you can keep track of which nodes you're visiting as you go through the breadth first search. So if the node 0 gets placed on the queue first, then the next iteration for doing breadth first search, I want to add into the end of the queue all the neighbors of the current node I'm looking at. So if I'm looking at node 0, then I'll add its neighbors 1 and 2, and in that order, because that's how they appear in the linked list. For node 0, I see the node 1 first, and then I see the node 2 next in the linked list. And I place those into the queue. And I mark them as visited. So I'm keeping track of which nodes I've seen so far in the breadth first search. And then I move, in the next iteration, I take the next node that's at the front of the queue. So since we've finished processing node 0, and in my queue I've got node 1 and node 2, but the next one at the front is node 1, I'm going to do the exact same thing for node 1 that I did with node 0. But the issue in the original graph is that if I look at what the nodes are in the linked list for 1, we've already visited node 0, so I don't have to visit it again. It does not get placed into the queue. And I've already visited node 2 because it was a neighbor of node 0. So neither will it be added to the queue. Okay, so then we're done with node 1. There was nothing else to do with it. We move on to the next node at the front of the queue, which would be node 2. Then we're going to do the exact same thing we did with nodes 0 and node 1. And we look at what are the remaining neighbors of 2 that we would place at the end of the queue. And there's only the one left. It's node 3. So we would go to place node 3 at the end of the queue. So as I'm doing all of this, if I know that I'm working with a graph that's, I can traverse from one node to any other node, it's a completely connected graph as input, then I know in my breadth first search that I'm going to visit every single vertex once, or every single node. And so the size of my queue, I can limit it to just be the number of nodes in my graph. It's very nice. So that's a linear amount of space needed for my breadth first search. Okay. While you're going through the process with this queue like this, you would have another array and you would call it your parents array. And if you think back to the very beginning of the semester, we had our union find and we had the parents array. And that's exactly how you can quickly store the information you would need for your resulting tree for your breadth first search. So it actually turns out to be a very quick little bit of code. It's not that many lines. You just have the one method inside your graph data structure, call it breadth first search, and it's about 5 or 6 lines within a loop. You have 2 arrays. One is your queue, and the other one is your parents array to keep track of your tree. And then you can return another graph based off of the information in your parents array. So I'll quickly write down what the parents array looks like here for the tree. Part of the reason that we've got this vertex 0 showing up, and I had the loop before, and I would want to get rid of that. When I go to build my tree, if you remember correctly, with our union find, when we had our parents array, if we have an index for each node, 0, 1, 2, 3, we kept track of which node was the root of the tree, and I'm going to consider this to be where the breadth first search started. So that was the very first node that we placed into the queue, which was node 0. I will consider the root for our tree. So we stored that in union find. We just gave it the same node as itself. So you're looking for within the array which index has its own number, and that gives you the root for the tree. And I won't go into the detail that they talked about in union find, where you could store a negative number and have the size of the tree that way, and you can also indicate that that's the root that way. So there's different techniques you could consider if you were going to do different functionality. So remember, you've got a lot of tools in your toolbox now. And then if I look at the parent for node 1, while I was doing breadth first search, we had processed node 0, and we saw that the neighbor we added to the queue would be node 1. So then I would indicate that node 0 was the parent of node 1. Similarly for node 2. And then lastly, we have node 3, and when we were iterating, adding, and processing to the queue, we were looking at node 2 at that time when we added node 3 to the queue. So that would mean that node 2 is the parent for node 3. And then I can use the information in this array to build my linked lists for my graph for the tree, for the output for breadth first search. So I'm going to pause again, and then I'll bring up a little bit of the code. You'll find out that it's actually quite straightforward. There's not a lot to write. And it's another reason I really like getting into graphs as a data structure near the end of the semester. It's like, oh, we've done all this hard work with hash tables and binary search trees and AVL trees, and all of those things are quite complex in order to manage the data. But with graphs, we just want to get started with them. And they're actually pretty nice to work with. Okay, so with the code, I'd like you to write this and just get more familiar with what's there. It's not a lot to type out. You will need a way of keeping track of some number of nodes, and each node has its own individual adjacency list. And remember, that's just, each one of those is a linked list. So you could have an array of linked lists, but we might want to adjust the number of nodes in our graph. And so we could introduce a new node by adding another linked list to this collection. And so it makes a little bit more sense to have this stored and managed with an array list. Okay, we get that, and this is, at this point in the semester, you're starting to get near the end. You're going to move on from data structures and algorithms, and it's like, oh, remember, you've got all this stuff inside the Java library. A lot of the things we've been talking about. So now it's much more appropriate to go grab those things to help support you. And you're always going to want to scrutinize what's the run times when you go to make a method call from these data structures you're using. So you will want to think back to, yeah, what's the efficiency of your code every time you're going to use these to help build up and layer on more complex data structures that you might create for yourself. So with the array list, it's nice because I don't have to worry about a limitation on changing the number of nodes. So I can always add another linked list to this collection. And I call it the adjacency lists because it's keeping track of the connections between nodes for me. Now for node 0, it will be the first one stored in the array list. So the first linked list. And so when I go to create a graph, we've got the constructor here. How many nodes am I going to have in my graph to start with? And the name for the variable size, you have to keep in mind that the vocabulary for graph data structures is a bit different from the other data structures we've worked with. And when they talk about the size of a graph, it means the number of edges, not the number of nodes. So we start off with 0 for the size. Because there are no connections when I first create my graph, I have to actually make those by adding them to my linked lists. Okay, but first we have to ask to create those linked lists for each node. So I iterate for the number of nodes, and I just use the other term for node, I'm going to add a vertex. Okay, if we go down to, I'm going to skip the other constructor here for a second. And we've got add vertex. What is it doing? It's going to create a new linked list for me, and it's going to place it into the adjacency lists collection. So I've got my array list taking care of that. So I'm going to have a new linked list for every node, but it doesn't have anything in any of those linked lists yet. So this constructor is simply creating a graph with n nodes, and there's no connections between those nodes. But it would be a good place to start when you look at the application code, because then I can start specifying what connections would I like between my nodes. And I've got those lines of code there. Whenever I'm applying the method connect and giving it the 2 nodes in the parameter, then I'll usually always list off the lower numbered label for the node. So I'll give 0 first and then 1 for giving the connection between the nodes 0 and 1. Similarly for the others, you'll notice that I'm always placing the lower number label. And you don't necessarily have to do that. And let's go take a look at the method to connect 2 nodes. If I pass in my 2 parameters, the typical names for nodes when you're working in graph theory, both in math and in computer science, is they work with label for a variable like u, v, w, t, x, z, y. They tend to select the letters near the end of the alphabet just to help everybody. It's a convention so that they are just reminded when they're working with a lot of different variables that, oh yeah, this is a vertex. And it's usually always lowercase. If I'm going to create the linked lists for these, well, I've already got them created, but I have to grab those from the array list collection. So that's the first thing that I do here. Let's take a look at that. I've got the get method to just simplify that a little bit because I don't want to write with the linked list its name and then .get and then pass it in. It's a little bit more typing everywhere else in your data structure. If you can simplify that a bit, you should. And I can just reduce it to get, because if I'm passing in a vertex variable, then it's really clear that I'm getting back the linked list for it. So I'm going to grab those, and then the names for it, I'm just going to call it U and then capital L for short. And for each of those linked lists, if it doesn't currently contain, say, the label for the first one, let's say, for example, vertex or node 0, if its linked list does not contain the connection 1, then I will add it. So if we don't already have the edge, I would like to add it, and I don't want any duplicate entries in my linked lists for the connections. Now you could have graph data structures with multiple edges between some pair of nodes, but that gets into a more complex kind of graph. So we're only considering working with what are called simple graphs. It's only possible to have one edge or one connection between any pair of nodes. Okay, if you've got the connection on the adjacency list if we've got the adjacency list for 0 and we add 1 to it, we also want to do the connection the other way around. So the linked list for 1, we would want to add the node 0 to that linked list. So I draw a nice picture. Of course, when we add an edge, we're going to increase the number of edges. And the edges that I've got in my picture kind of simplify what's going on in the data structure. If I really would draw everything, I'm going to check my color. In the data structure, what we've really got are directed edges. But I'm never going to talk about, when we move on to more discussions later, I'm never going to draw our data structures with directed edges because that's a little bit more complex. But just keep in mind that in the graph data structure itself, because we've got it showing up both ways, it's really keeping directions. So from 0 to 1, and then an edge going back 1 to 0. And if you're going to traverse from one node to the other, you have to be able to go both ways if we have an undirected graph. And I'm just going to stick with calling what we've got simple graphs. So there's no loops, there's no multiple edges, and there's no directions on the edges. But in the code, unfortunately, with the linked lists, you would really want to think about it. You're going both ways, given any edge. So it's almost like you're doubling up the information, and it might seem a little bit bizarre, but it's just because to facilitate the kinds of algorithms we do with graphs, if you want to traverse from one node to the other, yeah, then you really do have to consider the directions on the edges. And with simple graphs, we can always go both directions. So to draw it, I don't have any arrows, and I'm just going to know that I can travel from one node to another. Okay, I think I'll leave it here. There's any other simple description that we might have for this code is just the other constructor. So you can see I want to build up my tree for the result from breadth first search, and I'll have a separate video going over breadth first search. But if I want to pass in the parents array that we have, I'm creating a new graph, so that's why I've got this other constructor. We're passing in the parents array. We're going to create this tree. So it's a graph instance. Size, we haven't added any edges yet. We have to create array lists, one for each node. So it's very similar to the code we had before in the other constructor. And then we want to loop through the parents array. But how do I get rid of my bug? Well, it's just the one case where we've got the root, and we don't need to store the adjacency for the node that has the same label in the adjacency list. because we don't want to have any kind of loops where the edges loop back on the same vertex. So all I do is just test for if, and then we want to check parents, and we do I equal to I. And of course, I want the connections for everything but, so I'm going to do not equal to. Let's go and compile. Let me bring my code back, or my terminal back over to the other screen. Let's clear this out. We'll do java c star.java, and then java app. And there you go, it fixes the bug that I had. So you have to keep in mind, even with these more complex data structures, you still have to scrutinize the output and do your due diligence. You're always going to have to do debugging when you're programming. The other last thing is that I commented last week when we met in class that we've got some very interesting things going on in industry where a lot of people are pair programming with AI, which just accelerates how quickly you can write code. And again, you can really only do that if you're understanding what you're doing. Well, for the most part, I think you can work a lot faster, so you get the advantage from the AI if you already know what you're looking to try to do, because you don't have to do all the typing yourself, and then when you go through, you can debug quite a bit faster as well, because the AI can also point out where the issues are if you're asking it. And you have to get really good at asking questions then, which makes you smarter when you think about good questions. And I'm considering, like, if you're looking at accelerating your learning as well, when you go to study on your own, we looked at using ChatGPT at the beginning of the semester, where you know it's really good if you ask a very concise question so that the output is quite small, so that you just get that one next step that you need in order to move your understanding forward, rather than generating a whole bunch of output and you don't understand everything that it's saying, and then you're trying to hunt for what it is you need. So I think people will get a lot more proficient at asking good questions. And I look forward to how education will likely change in the future, where we start to consider, especially in programming, working together with pair programming with the AI. So I would encourage you to explore that in your own practice, and you'll probably reflect on what is helping you to effectively learn versus what is doing things for you like a crutch, and then it's not really helping you.